Okay, hello everyone. Welcome to the final EE259 lecture for spring 2023. So last time we started talking about imaging and vision systems or cameras, and we briefly talked about the history of imaging, and now we're ready to start talking about the physics of imaging. So as we did for other types of sensors, we're going to start with the principle of image formation, which is pretty simple, as you see in this picture. So typically you have some object out in the field, and then your imaging system or camera consists of some imaging optics, which is an assembly of lenses typically, and then rays of light basically pass through your optics and come to focus on an image sensor. So this, for instance, used to be a film in traditional film cameras, but in the modern cameras, these are digital image sensors that we'll talk about in detail. And the sensor basically, or the digital image sensors, consists of many pixels that measure light intensity, and they can do that at different wavelengths. So color cameras, for instance, have pixels that measure light intensity at red, green, and blue wavelengths, or RGB. But you can also have other types of cameras. For instance, thermal cameras measure light intensity at long wave IR, which is, in 6 to 12 micron range in wavelength. And then what happens after that, basically, there is some signal processing engine or image signal processing engine on the camera, called ISP for short, that collects the signals from all the pixels and combines them and processes them to form an image, which is what we get out of the camera. So the first thing you might ask is, why do we need the lenses or the imaging optics? Why can't we just put the sensor in front of the object and have an image formed on it? And the reason is basically explained in this picture here. So without optics, what happens is that every sensor pixel would basically receive rays of light from every point on the object, and it would record basically the integral of light arriving from every point on this object. So then essentially what happens is that all sensor pixels would record a similar color and similar intensity, so you get a complete blur. And that's, for instance, why we don't get images formed on walls or other diffusely reflective surfaces, because there is no optics. Every point receives light from everything out there, and there is no image to be seen on them. So that is why we need the imaging optics, and basically the job of a properly designed lens system is to make sure that every point in the subject, or the rays coming from every point in the subject, get focused properly on a point in the image sensor, the image plane, and then we get like a nice sharp image formed. Now, at the core of the image formation principle is this idea of exposure. So what exposure is, mathematically denoted by H, it is the amount of light energy per unit area that reaches the surface of the image sensor. Okay, so there's two factors contributing to the exposure. So our exposure is the multiplication of basically the power density, or the optical flux density, that is hitting the sensor surface. That is denoted by E, and it's called irradiance in the in the optics field, and it's basically, for us, it is because we know about the theory of electromagnetic waves. The irradiance is basically the magnitude of the Poynting vector, which, as we know, is basically the power flux density of an electromagnetic wave. So it has the units of watts per meters squared. So that's the first factor that contributes to the exposure. And then the second one is the time duration that every pixel in the sensor is exposed to light. Okay, so that's T, which is the exposure duration. We multiply irradiance by the exposure duration, and that gives the total exposure. Now, these two factors, E and T, they can be independently controlled in an imaging system. So irradiance is typically controlled by the aperture size of the optics or the lens system, right? So the larger the aperture opening is, more light is going to be let through, which increases the irradiance on the image sensor surface. And then T is basically controlled by the shutter speed. So basically, every system you can set the time duration that the sensor is exposed to light per frame of image that you are capturing. So then, because you can control these two factors independently, then for the set amount of exposure, you can have different combinations of aperture size and shutter speed that give you the same exposure. So you can increase your aperture size and reduce the shutter speed, or the other way around, reduce aperture size and increase shutter speed and keep exposure the same. But it turns out that doing like changing the aperture size and the shutter speed while keeping the total exposure the same would have very different effects on the final image that you get. Specifically, what increasing the aperture size does to the image is that it reduces the depth of field. Okay, so here if we look at the two images on the top row. So these are two images captured of the same scene. And between the two images, the total exposure is the same. As you can see, the colors look the same, the intensity looks the same. So it's the same exposure. But what has changed between the two is that the left one has a large aperture opening and the right one has a small aperture opening, which means to keep the exposure the same, the left one had a faster shutter speed or smaller exposure duration, and the right one had a longer exposure duration. But because the scene was a stationary, that the time didn't have an effect on the final image, but the effect of the aperture opening, as you see in the left one, the background is completely blurred, versus in the right one, we get like a nicely sharp focused background. And that's the idea of depth of field. So we'll talk more about it, but the general trade-off is large aperture openings lets more light through, but reduces the depth of field. And the depth of field is roughly speaking is basically the range of distances for which the subjects will be in focus in the final image. Now, let's talk about reducing shutter speed. So reducing shutter speed, the effect that it will have is that it will increase motion blur in the final image. So if we look at the bottom row here, again, there's two pictures of the same scene with the same amount of exposure. But between the two, the left one has a slow shutter speed and the right one has a fast shutter speed. And here the scene, unlike the top one, was not stationary. So the hand and the hammer were moving as the shot was taken. And the slow shutter speed causes, as you can see, significant motion blur in the scene versus the fast shutter speed kind of like freezes the moving subjects in place and basically makes a sharper final image. The depth of field effect is also there. Like if you look very closely, the one with the slow shutter speed, to keep the exposure the same, it means that the aperture size was smaller. And if you look at the background, the wood grains are more in focus in this one compared to the right one, which is kind of it looks a little softer or more out of focus, and that's the depth of field effect. So these effects always exist and go hand in hand. And so what's the right choice? Well, it depends on the application. There's really no right or wrong here. It really depends on, like, do you care more about depth of field or do you care more about the sharpness and the motion blur, and for your application, and what is the right trade-off to make there. Okay, now when it comes to exposure itself, it turns out that there's always, for every given scene, for the given, dynamic range and the lighting conditions, there's always a correct amount of exposure. So that's the total energy density of the light that hits the sensor within one frame. And that's the correct exposure is such that basically the highlights and the shadows in that scene kind of show nicely in the final image. So if we do less than the correct amount of exposure, so if we underexpose the image, that's the case where not enough light reaches the sensor, and in that case, especially the shadows would look too dark or maybe completely black, and we lose all the details there, which is the case in this image. You see, like the darker areas, there's not a lot of detail because of underexposure. And then the opposite side of it is the case of overexposure, and that's where there's too much light reaching the sensor, and in that case, the highlights or the bright regions of the image can get washed out or completely saturated if we hit the dynamic range of the sensor, and then we lose all detail. As is the case in this right image, as you can see, you know, the sky and the bright areas of the scene are completely washed out, and we have lost all detail. And then this middle one has the correct amount of exposure where everything is nicely exposed. Now, it's not like there's just one value of exposure that is correct. I mean, if you look like this one to the right and to the left of the middle one, one is a slightly overexposed, the other one is slightly underexposed, but still you can make out all the details in the scene. So there is, you know, there's a bit of a margin there, and especially when it comes to artistic photography, you know, different people have different tastes. Like I myself, I'm not a big artist, but when I take photos, I tend to underexpose a little bit because I like to exaggerate the shadows a little bit. Now, when it comes to autonomy, modern cameras, almost all of them have algorithms that try to, by you know, some sensing from the scene, from like the total intensity that they're getting and things like that, with some heuristic algorithms, they try to automatically set the correct exposure level. And in most cases, it works reasonably well, but they're not perfect. In certain cases, especially scenes with very high dynamic range, they need to, you know, make a trade-off, or sometimes they just flat out make a wrong decision. So just note that auto exposure exists in all modern cameras, but it's never perfect, but it works reasonably well in most cases. Okay, so that's about the high-level physics of imaging. As we said, a big part of, a very important part of any imaging system is the imaging optics, or the lenses. So now we're going to talk a little more about lenses. If you remember, we did talk about the lenses in the context of LiDAR and Gaussian beams, and the importance of lenses for, you know, proper collimation of beams. Here we're going to look at lenses for a different application, which is image formation, and we're gonna develop a different framework which is more useful for understanding the physics of imaging, and the framework is called geometric optics, as we'll see. But at a high level, again, what a lens system or imaging optics does for us, as is shown in this bottom example, is that it makes sure that every point on your subject, or the rays of light that are coming from that point, they nicely get converged or focused on a point in the image plane, and that means we get, you know, a nicely focused, sharp image form, versus anything else that you try to do. I mean, we talked about having no lens at all, and then you get just a complete blur. You don't even have an image. But other things, like if you put like a tiny pinhole, and try to, you know, just restrict the small rays of light to go through that, even a small pinhole, it's not going to be perfect. There's going to be, you know, every point is going to form a small spot instead of, you know, a nicely focused point in the image, and then you get, you know, with a pinhole, you get a blurred image. Just to note, I mean, pinhole photography is a thing, and there is techniques that can make very nice images with pinholes, but they come with very big trade-offs. So in practice, I mean, for artistic photography, they're used, but in practice, you know, for sensing application, nobody uses pinhole cameras. Basically, everybody uses cameras with optics. Okay. So with that, when it comes to understanding the properties of lenses and their importance, there are two main physical parameters of lenses that basically affect the quality and the characteristics of the images that are formed. First is the focal length. And focal length, as we'll see, determines the field of view of the camera. You know, what azimuth and elevation field of view you get in an image. And then there is the second parameter, which is called the f number, or n, for the lens. And the f number, as we'll see, it determines the effective aperture size. And as we briefly talked, aperture size affects the depth of field. Right, and we'll talk in more detail about this, but at a high level, the focal length and the f number together determine the field of view and the depth of field of the image that we're going to get. Now, there's other lens parameters that some lenses have these, some don't, but generally speaking, you can have fixed versus variable focal length lenses. Fixed focal length lenses are called prime lenses, and then zoom lenses are the ones where you can vary the focal length. Every lens has a minimum focus distance, so if a subject is closer than that to the lens, it just cannot focus on it, and you would always, no matter what you do, get a blurred image. Some modern lenses have active image stabilization, so this is kind of like an active mechanical system that moves around some of the optical elements inside the lens to cancel out vibrations. It's kind of a relatively fancy thing. So many lenses that used in robotics, they just don't have it, but some more complex ones do. And then there are lenses that have perspective control. You might have heard of like tilt shift lenses, and these are mostly used for artistic photography and not really for autonomy applications. So we're not gonna cover this. We will mostly talk about these two characteristics of the lenses. We want to understand the focal length and the f number, and how exactly they determine field of view and the aperture size. Okay, as I said, the framework we will use to analyze lenses is called geometric optics. So what geometric optics is basically, it's an extension of this idea of paraxial wave approximation, which we developed as we were talking about Gaussian beams in LiDARs. Now, it turns out that you can extend that idea in the cases where the wavelength lambda is small compared to the size of the optical components. You can extend the paraxial wave approximation to what is called the geometric optics. And what happens in the geometric optics regime is that we now, instead of thinking of light as a wave, we just model light as straight rays that just travel in straight paths in homogeneous media. And these rays, they do bend at the interface between two dissimilar media. And by dissimilar, we mean like media that are different materials or have different refractive indices. For instance, they can bend these rays of light, which is exactly what, for instance, a lens does. But just note that the geometric optics is very useful to for instance, understand image formation physics. But it's an approximate framework. So, for instance, some effects such as diffraction or interference are completely ignored in the geometric optics framework. And again, it also completely and that's because it completely ignores that wave nature of light, which is, as we know, that's the underlying physics. But nevertheless, the framework is extremely useful for the purpose of understanding imaging systems, and that's what we're going to use. So when it comes to lenses and in this geometric optics framework, the operation of lenses, or at least I should say ideal lenses for now, can add non-idealities to the behavior. Ideal lenses, also called thin lenses, they behave very simply. So the way they're modeled is that if you have some parallel rays of light, as shown here, that basically are incident on the lens, they get converged to a point that is a focal length f behind the lens. So you basically take the center of the lens and then a focal length f away from it. All the parallel rays are converged to that one point. So that's one basically main result that comes out of the geometric optics. And then the other thing related to geometric optics and lenses is that if you have rays that go through the so-called optical center of the lens, those rays would not be deviated. So they just go straight through. And for ideal lenses or thin lenses, the optical center is basically just the geometric center of the lens, right? And again, as shown here, the rays that are pointed towards the optical center just go straight through with no bending or anything like that. Now, with just these two principles, it turns out that we can fully analyze like how image formation works, at least with ideal lenses. But before that, we need to discuss how what the focal length is and how it's related to the geometry of the ideal or the thin lens. The ideal lens, the geometry is very simple. For instance, if you have a double convex lens, the geometry is just described by the radii of curvature of the two surfaces. So you have a curvature radius of curvature RL1 for the convex surface, and you have RL2 for the concave surface. So those are the two radii of curvature. Note that the convention here is that the radius of curvature for convex surfaces, it's taken to be positive, and for concave surfaces, it's taken to be negative. So in this case, this surface is the convex surface. So RL1 is positive, and RL2 is negative. Because this second surface is the concave surface as the rays, going in this direction. Now, with this definition and this geometry, the focal length is a function of the two radii of curvature and also the refractive index of the lens material, which could be glass or plastic or other materials. And this is the equation. So 1 over f is n-1 times 1 over RL1 and minus 1 over RL2. Remember that the refractive index n is the square root of the relative of mu r times epsilon r, where mu r is the relative permittivity and epsilon r is the relative permeability, which is equal to c over v, where c is the speed of light in vacuum, and v is the speed of light inside the material, the lens material. So that's the speed of light inside the lens, whatever that material is. So basically, light gets slowed down by a factor of n when it's traveling inside the lens. Okay, so that's how for a simple ideal lens like a double convex lens, how you can find the focal length. Okay, now with that, and with the two principles that we talked about parallel rays hitting the lens, getting converged to a point, a focal length behind, and rays that hitting the optical center going straight through, now we can kind of have a very simplified model using geometric optics of how image formation works. So here we assume we have this ideal lens, and then it's a 2D picture, but it works the same in 3D. So we have some object or a point on an object shown by the tip of this arrow, basically. And the rays that are rays of light that are coming from that object, basically, all of them get converged to a point on the image plane. So they all basically get focused. And again, the parallel ones that hit the lens, they go through the focal point of the lens. So that's the point which is a distance f away, and then the ray that is going through the optical center goes right through, and then the point of intersection of those points of those rays is basically the focus point on the image plane. And any other ray that we basically launch from that target is going to go, in the ideal case, through the same focus point. So all the rays basically get converged in one point. And this basically method of analyzing image formation is also called Gauss's ray tracing image construction. Okay. Now, in this geometric view, we need to basically understand the main thing is kind of like the distance between the object to the lens and the distance between the image to the lens. So we need to be able to find those distances, as well as basically the height of the image point relative to the height of the object, which is kind of like a magnification factor, if you will. Okay. Now, by a pure geometric analysis, and by this I mean just looking at similarities of triangles and things like that, which I won't go through it, but it's a very simple geometric analysis. We can come up with the Gaussian lens formula, which relates the distance between the lens plane and the object, and the distance between the lens plane and the image, and the focal length of the lens. And it's given by this very famous simple formula, which is 1 over SI. SI is the object distance to the lens, plus 1 over SO, where SO is the image distance to the lens, equals 1 over the focal length. One thing to note is that these quantities, SI and SO, these are signed distances. And for SI, the positive is rightward, right? So in this specific picture, SI is positive. SO is also positive, but for SO, positive is leftward. Now, for very specific cases, like special types of lenses, SI, for instance, can become negative, and that's where we have like a virtual image that is formed in front of the lens instead of behind the lens. So just note that those are signed quantities with different positive directions. And also we can find, by again a purely geometric type of analysis, the ratio between yi, which is the height of the image point, to the yo, which is the height of the object point. And we call that MT, which is the lateral magnification factor. So that's YI over YO. And YI and YO are also signed quantities. And here, positive is upward for both of them. Okay. So with that convention, YO is positive, YI is negative, because the image always comes flipped relative to the object, and because of that, yi is negative. So the lateral magnification yi over yo becomes equal to negative si over so. And again, these things, like these equations, are very simple to derive. Maybe just just to convince you, like these are from pure geometry. Like this one, you get it just by the similarity of these two triangles that I'm going to highlight in blue. So this one and this one. these are two similar triangles, and the sides are of length yi and yo, and then this is so and si. So just by similarity, that gives you this equation here. Okay, very good. So that's basically with the geometric optics framework how image formation works. But the question you might ask is, what if you're not working with a simple thin lens? What if you're working with an optical system that contains many lenses? And that's the case for many modern optical systems, like even, you know, small, tiny digital cameras, like the ones in the phones these days have optics that consist of like multiple lenses, 4, 5, 6 or so lenses go into it, and those are not the simple, you know, picture that we analyzed here, and they're called or they can be modeled as the whole, you know, optical assembly containing all the lenses can be modeled as one thick lens. Okay, and thick lenses can be characterized by a few parameters. We're not going to go through the full details. So instead of just the focal length and, you know, the radius of curvature, there's multiple parameters that go into, you know, the description of or the model of a thick lens. So there's like the secondary principal plane, the primary principal plane, and basically, so in a way, you have, you know, a different focal point f prime behind the lens than another one in front of the lens with different, you know, distances. So you have f prime and f. But at the end of the day, again, there's a link here that describes the full, you know, characterization and the model of the thick lens. But the same ray tracing principles apply to the thick lenses. So if you have an object and then you basically trace the rays of light that come out of a point and the object, they do get converged to a point on an image plane. So essentially, at the end of the day, it's the same principle of image formation, but the geometry and the, you know, and the model becomes a slightly more complicated, not even too much complicated. Okay, so everything we talked about, we did it for like a simple thin lens, but bear in mind that it applies to more complex optical systems also. Okay, so one thing, I'm going to just go back to this picture here and clean this up a little bit. So if you look at this Gaussian lens formula here, this one, this is telling us something very important. Again, if you go beyond the math, right, and just think about what it means, right? What does this imply about the physics of imaging? One thing we can see here is that if we fix the focal length f, okay, and we also fix the position of our image sensor, meaning S sub I is fixed. We just have, you know, a sensor at a fixed position relative to the lens, and that's SI, and that is fixed, and we're not going to change that. With those two parameters fixed, that means SO would also become fixed. The SO that solves this equation becomes fixed. And what that means is that for a lens of fixed focal length and a fixed position of the image sensor, only objects in one specific plane out in the field would become perfectly focused in the image plane. Any object with an SO that is not the one that solves this equation would be out of focus. So if you have another object slightly, you know, in front or slightly behind that main object, those two still form something on the image plane, but it's not going to be in perfect focus. Okay, and that's a very, very important principle to note. Okay, so then what can we do to change that focus distance? So if we want to, you know, bring objects at different distances from the lens into focus, what should we do? Okay, if the lens has a fixed focal length f, again, for that, only objects at a specific distance are in focus. So in order to focus on objects at different distances, we need to move the sensor, right? So relative to the lens. So we have to move the sensor relative to the lens, and that's the picture that's shown here. So when the sensor is exactly at the focal plane of the lens, so that's where SI equals to F. If you go back to our Gaussian lens formula, which was 1 over SI plus 1 over SO equals 1 over F, that means 1 over SO should be 0, which means SO equals infinity. So when the sensor is at the focal plane of the lens, we are focusing at infinity. Okay, that's one case. Now, as you start moving your sensor back, the focus plane starts getting closer and closer to the lens, right? You move your sensor even further back. Now your focus plane is closer, and then at some point, you basically, if the focus plane is at the focal length, so if SO equals F, that means SI should equal infinity. So that means you have to put your sensor infinitely away from your lens to be able to focus at the focal length in front of the lens, which basically means you cannot do that. So you cannot focus on objects closer to the lens than its focal length, right? And that's kind of like that idea of the minimum focus distance for a given lens. Okay, so this is important to note, that in order to focus at different planes out in the field, you need to move the sensor relative to the lens. Another way of thinking about it, which I really like this way of thinking about it, which is given in this box here, is that lenses actually transform a 3D object or a 3D scene into a 3D image. So the actual image that is formed behind the lens is a 3D image, right? But because we have a 2D sensor, just a sensor in a plane, we can only extract a 2D slice from that image, right? And that slice is where you put your image. So we just extract a 2D slice from a 3D image, and in that slice, only objects that correspond to a specific distance from the lens in the physical world are in focus, and everything else that is closer or further away is going to be out of focus. That's another way of thinking about it. Okay, so that's about changing the focus distance. Another thing we need to discuss is, what about changing the focal length? Okay, and you can change the focal length by changing the lens entirely, or, as we said, some zoom lenses have moving optical elements inside them, and for instance, with a ring or some other control mechanism, you can vary the focal length of the lens in some range. So lenses that have larger or longer focal lengths, those are called weak lenses because they bend the light less. Okay, so weak lenses have longer focal lengths. And as you see in this picture, so here we have a system, and first we were using a lens with a focal length of, say, 3 inches, and then to bring this plane in focus, which is where the tree is, we had to place our sensor at a certain distance away. Now, if we use a weaker lens keeping everything else the same, so now we go to a focal length of 6 inches, for instance. In order to focus on the same image plane, we need to move the sensor further back. Again, because this is a weaker lens and it's bending the rays of light less, so the point that those rays converge are now going to be further away from the lens. Okay, but another thing that happens, which is very important here, is that, okay, so we need to move the sensor back with the longer focal length to get to focus on the same subject, basically. But if the size of the sensor remains the same, which is almost always the case, okay, now we're going to have a smaller field of view, as you see from these ray tracing here. So at the top one, the field of view is like the topmost pixel on the image, we just pass it through the optical center of the lens, and that's hitting, kind of the base of the tree. And the bottom pixel, if you trace the ray that's hitting that, it's getting the top of the tree. So our field of view covered the entire tree, right? Now, with the weaker lens and the same sensor placed further back, if we trace the ray from the top and bottommost pixels, we'll see that it only covers the midsection of the tree. So that means our field of view got reduced, right? So that's the effect of changing the focal length. As you increase the focal length, the FOV goes down. Or another way to think about it, it's kind of like a zooming effect, right? Now, with the longer focal length, just the centerpiece of the tree is going to cover your entire sensor. So it's kind of like you're zooming in, and that's why these lenses with variable focal lengths are called zoom lenses. Here's a picture I'm showing, for instance, for how this effect works. So here we have a fixed scene. So that's the scene. It's some like a harbor, but with some buildings and people and ships around it, and the camera was placed at a fixed position in the harbor, and the subject or the scene is also constant, and all we are changing is the focal length. So a zoom lens was used, and the focal length was changed. So first we start with a short focal length of 17 millimeter, which gave us a very wide field of view. So as you see here, 17 millimeter can basically that gave us 140 degrees field of view. And then we start, kind of zooming in or increasing the focal length. So as you go from 17 millimeters to 50 millimeters, now your field of view gets reduced, and it only gets roughly, if I can get it here, it only gets like this part of the scene. So that's what you get from a 50 millimeter field of view. Now, if you go from 50 millimeters to 135 millimeters, you further zoom in, and now you only get maybe something like this part of the scene, right? And that's what this picture is, right? So you're reducing the field of view, sensor size is constant, so it feels like you're zooming in, right? And then if you go from 135 to 500 millimeters, so now we are at 18 degrees, right? Now, if we go to 500 millimeters, we further zoom in to something like just this. And that's what we get. And that's just a 5-degree field of view. So you see, as we went from 17 millimeters to 500 millimeters, we reduced our field of view by almost a factor of 20, right? It went 20x down. So it's a kind of a nonlinear effect between focal length and field of view, and it also depends on your sensor size. So it's not this ratio. Yeah, it can be different for different lenses and different sensors, but that's the high level effect of how changing the focal length affects the final image. It basically controls your field of view or zoom factor. Okay, so that's about the field of the focal length and the effect it has on the pictures. The second important lens parameter, as we said, is the f number, which controls the aperture size. So the f number n of a lens with aperture diameter A is given by this. So n is the focal length divided by the aperture diameter. So the aperture diameter, remember, it's typically circular for lenses, and then A is the diameter. So f over A is the f number of the lens. So for instance, a f number that is f over 2 on a 50 millimeter focal length lens means that the aperture diameter is 25 millimeters. Okay. So remember, one of the factors that affects the total exposure of pixels on the image is irradiance, or E. And irradiance is proportional to two factors. One is basically the total area of the aperture opening, so the total area of this circle. Okay, that's one thing. So that's basically how much light is coming through. and the area is proportional to the square of the diameter, right? So again, this is aperture area, or proportional to aperture area, and that affects the irradiance. And the second thing that affects irradiance is it's inverse, proportional to the inverse square of the distance between the sensor and the lens aperture. Right. And the distance, as we know, it varies. It depends on, where we are focusing at. But roughly speaking, it's about a focal length. It's kind of usually close to F. It's not exactly F, but it's close to F. Okay. So our total irradiance then is from these two is proportional to A squared times 1 over F squared. Right. And then from this formula, it means it's proportional to 1 over N squared, or the F number squared. Right. So that's how our F number affects the total irradiance, or the total, light energy per unit area that hits the sensor within one frame. So increasing our F number by a factor of K would reduce the irradiance by K squared. Okay. And that's an important trade-off to note. Now, as we said, the aperture diameter, or aperture size A, affects the depth of field in the image. And that's one thing we need to, study and quantify, and exactly first define what we mean by depth of field, and then how we quantify it and how it's affected by the aperture size. So the way depth of field is defined is kind of this idea of using this idea of permissible circle of confusion. So remember that we just argued that for any given imaging system, only points in just one object plane, which is at a very specific distance from the lens, will be perfectly focused in image, right? So for a given focal length, given distance between the sensor and the lens, only one object plane, one SO, would come to perfect focus. Okay, and points in any other plane or any other distance from the lens will form spots in the image. Instead of like getting focused to points, they form, spots on the image. But it turns out that for all practical purposes, if those spots are small enough, we can consider them almost in focus. Okay, and that's this idea of permissible circle of confusion, or C, which is the size of the spot on the image that is considered acceptably sharp, okay, or almost in focus. And the C, there's no, formula that we can give and say, oh, okay, so this is how you calculate C, and, if any spot is smaller than this, it's in focus, and larger than this, it's blurred. It depends on a lot of factors. So it depends on the sensing medium. It depends on the reproduction medium, like is it printed? Is it on a display? Is it on a projector? Is it on a TV? It really matters. The viewing distance also matters, like how close are we, depends on the vision of the human who's looking at it, how good their vision is, and other factors, right? So it's quite subjective, what at the end of the day what the circle permissible circle of confusion is, but typically for digital sensors, C is taken to be the size of 1 pixel. Which, for instance, for different sensors is different, but for instance, for a DSLR camera, it's about 6 microns. Okay, and that's what is taken. So if the spot is less than this pixel size, again, because that's our unit of measurement, we can't even measure anything that's less than the pixel size. So we just call it, okay, that's perfect focus, which kind of makes sense. And now in other cases, it can be that C is taken to be more than a pixel, but that's typical. And this C can then be used to determine the depth of field, called D. And the depth of field is basically a range of distances from the lens that all subjects that fall within that range of distances are, reasonably in focus or acceptably sharp. And that's what we call the depth of field. So here, this picture is kind of, illustrates this concept of permissible circle of confusion. So if we start at and look at the middle of the picture first. So here's, the object plane at which the points come to a perfect focus on the sensor. So this is our sensor plane, and that's our object plane that is perfectly imaged. So then this is if that's our excuse me, lens plane, this is our SO and this is our SI, right? And that's perfect. And you get like a perfect point, perfect focus on the image plane. Now, for objects that are closer or further away, as we argued, what they form on the image plane is spots, right? And if these spots are smaller than or equal in diameter to C, which is the permissible circle of confusion, we call them acceptably sharp, right? Same for objects that are further away, they're gonna form spots, and if the spot is smaller than or equal to C in size, we call it acceptably sharp. So with that means we can then have a range of distances, which we call D, or depth of field, and of course the object plane is within that depth of field, the perfectly focused object plane. But everything that's within D out in the field is considered reasonably sharp and in focus in the final image. Okay, so how do we calculate D? Well, it turns out that, again, just like we did the Gaussian imaging formula, with pure geometric arguments, we can also quantify what the depth of field is for a given permissible circle of confusion. So here's the picture here. And again, D is the distance between the nearest and the furthest objects that are acceptably sharp, focused in the image, or they form spots that are no bigger than C in size. Okay. Yeah, we are not going to go through the full, geometric analysis, but note that it's pure geometry done here to derive what D is. So this picture kind of shows so on the image plane, this is the permissible circle of confusion. That's the green is the diameter of it. And then you can translate that to what is called the conjugate of circle of confusion, which will have a diameter that is C divided by MT. And remember, MT is the lateral magnification factor, okay? And the lateral magnification factor, it can be roughly approximated by U over F, where U here, as you see, is the distance from the lens to the perfectly focused object plane. That's U, and F is the focal length. So the conjugate circle of confusion has diameter C over F, and then this diamond-shaped basically area, that is kind of, or the distances of the two ends of it from the lens, that's what our depth of field is, right? So from our image plane, you can come forward a distance D1, and you can go back a distance D2, and you would remain in focus. That's the idea. And notice that it's asymmetric, right? So the perfect object plane is not in the center of the depth of field. That's very important, right? So it's like this diamond has asymmetry in it. And specifically after solving the geometry, D1 we can show is equal to this, which is N times C times U squared, where N is the F number, C is the permissible circle of confusion, U, remember, is the distance between the in focus object plane and the lens, divided by F is squared plus NC, where F is the focal length. So that's D1. And D2 is given by this other expression, which is NCU squared divided by F squared minus NCU. Okay, so again, note the asymmetry in the depth of field. So what is the total depth of field? That's just D1 plus D2. We add the 2, and this is our final formula for the total depth of field that we get for, and it's a function of many parameters, right? You see the F number and goes in it. Of course, the circle of confusion goes in it. The distance to from the lens to the in focus object plane goes in it, and the focal length goes in it, right? So all of these parameters at the end of the day can affect our depth of field. Now, this formula, this is the most accurate version of it, but in many cases, it turns out that the conjugate of the circle of confusion, which has the size C over MT, is small relative to the lens aperture A, which is F over N. And in those cases, this N squared C squared U squared term in the denominator can be ignored, okay? And then we get a simpler expression, which is this. So the depth of field is approximately equal to 2nCu squared over F squared. Okay, so let's remember that this one is approximate, but it's a very good approximation for in many practical applications. But you should always check that, like, this is this condition is C over MT, smaller than A or not. If not, you should use the more accurate version. Okay. Now, with this, we can see, as we said, there's multiple factors affecting depth of field. Number one is N, or the F number. As we saw before, it does affect the depth of field, and it affects it linearly. So, right? So it's linear in F number. It's quadratic in U, which is distance from the lens to the in focus object plane, and it's inverse quadratic in the focal length, right? So if any of these parameters changed in our imaging setup, it's going to affect the depth of field. Let's look at some examples. We start with F number. So as we said, depth of field varies linearly with aperture size, which is controlled by the F number, right? So here's two pictures of the same scene taken with different aperture sizes. So first one, we were doing N is F over 2, which is a large aperture. And then the second picture is taken with N is F over 16. So we reduced the aperture size by a factor of 8. So it went 8x down, right? Or I should really say 1 over 8, right? That's how much we reduce the aperture size by 1 over 8, right? And we know the depth of field is linear in N, so increasing N by a factor of 8, right? So we increased N by a factor of 8, which means aperture went down by a factor of 8, should increase our depth of field by a factor of 8, roughly. And that's exactly the case. So we kept everything else the same. So U, which is the the distance to the plane of in focus plane, that was kept the same. So in both cases, we were focusing on the face of this middle person in the scene. So to keep the U the same, focal length the same, everything was the same. And with the small aperture, the depth of field was just about 1 foot. So as you see, just the main target that we focused on is in focus, and then object in the front and the third person in the back, they're both completely out of focus. And then we increased N by a factor of 8, or reduced our aperture size by a factor of 8. And now we have a depth of field of 8 feet. Again, U is the same, so it's important to just change one parameter here. So that's U. But now with the depth of field of 8 feet, all 3 subjects are reasonably sharp and in focus. The middle person, the front person, and the back person. The back person, maybe it's not that perfect, but it's still reasonably sharp, like compared to what we had originally. Okay, so that's the effect of aperture size and on depth of field. The other 2 parameters that affect it, as you know, is the focal length and U, which is distance from the in focus plane to the object. Let's look how those affect it. So depth of field varies inverse quadratically with focal length. And that's illustrated in this 2 pictures on the top row. So here again, it's the same scene, same lighting and everything. And we have only changed the focal length of the lens that was used. So this one is long focal length, 135 millimeters, and this picture is taken with a shorter focal length, 50 millimeters, and depth of field is inversely proportional to f squared. So it's proportional to 1 over f squared, which means the short focal length should give a much higher depth of field, which is the case here. As you see, the front subject and the back subject are both in focus, versus with the longer focal length, the main subject that we actually focused on, of course, is in focus, but the back one, not in focus because the depth of field got reduced. Then the second thing to look at is the effect of focusing distance. So it varies, the depth of field varies quadratically with focusing distance u, and that's what is illustrated here. So again, everything is kept the same except u for this experiment. And first we have a small u, so the camera was just 3 feet away from the front subject that we focused on. And then we moved back, basically the camera moved back to 10 feet. And with that, we now get a longer depth of field. So both subjects are now in focus, versus in the first one, the back subject was out of focus. Okay, so hopefully with this, it's kind of clear how all these trade-offs work when different parameters affect the depth of field. So this kind of concludes the discussion about lenses. So we covered, the geometric optics, the image formation through lenses, and also we specifically talked about the focal length and the f number of the lenses, and how the f number controls the field of view of the image, and the n, along with other parameters, mainly controls the depth of field. Well, as we saw, f also contributes to depth of field. Okay, so that's about lenses. Next topic we want to talk about is digital image sensors and the physics of it and the electronics of it, and how these image sensors are built and operate. So there's different types of digital image sensors and different architectures and different constructions. The two main ones are called complementary metal oxide semiconductor, or CMOS sensors. So that's one semiconductor process and architecture that is used to build digital image sensors. And the second type is called charge coupled devices, or CCDs. Okay, these are both used, they're both deployed. And there's a number of trade-offs between these two architectures. So they have different noise levels. So for instance, CCDs are less noisy than CMOSs typically. The speeds are different. CMOSs are typically faster than CCDs. The sensitivity levels are different. Cost is different, and other factors. We will only study CMOS sensors in detail, because those are the ones that are mostly used in more cheaper, more robust imaging sensors that are used in robotics. CMOS sensors are more flexible, they're cheaper, and the performance is pretty good. It's maybe not as good as the best CCDs out there, but they're very good sensors. And here's one image of a 120 megapixel CMOS sensor from Canon, and that's what the thing is looks like. It's pretty small. I mean, this is a few centimeters in diameter, basically, and diagonally, basically. Okay, so let's talk about CMOS sensors. The type of CMOS sensor we'll talk about, it's called the active pixel sensor, or CMOS APS. And a CMOS APS consists of an array of active photosensitive pixels. Okay, so each of those pixels in the sensor becomes one pixel in the final image, basically. And each pixel consists of three main components. Okay, first is the photosensitive component in the pixel, which is a reverse biased PIN photodiode. So that's the part of the pixel which converts incident light or photons to an electrical signal. And this is exactly the same as LiDAR, right? So we in great detail. We talked about PIN photodiodes and why they're reverse biased, how they operate, what's the responsivity, and all that. So this is exactly the same. Different materials because, for instance, if you're making a visible light camera, you're not going to use an InGaAs, PIN diode, which is most responsive at 1550 nanometers. We will use silicon, but same physics, right? So we're not going to talk more about, the principles of PIN because it's exactly the same as what was covered in LiDAR. Then the other two components in every pixel of a CMOS APS is the readout circuitry. And the readout circuitry, what it does is that it kind of sends the signal, the electrical signal that you get out of the PD or the photodiode, and it sends it to the ADCs to be digitized. So that's the readout circuitry. And it needs to be architected and designed such that you can read out every pixel in this APS array. And remember that modern sensors have many, many pixels, right? You can have millions of pixels. So it's important to have, an architecture that can, nicely read out all the pixels without crosstalk or congestion or anything like that. And then there's a reset circuitry, and the reset circuitry essentially it controls exposure duration per image frame. Remember that, especially if you're taking videos, you want to take consecutive frames, and each frame you want to start clean. So you want to reset all the pixels and start exposure, and then at the end of the exposure duration, read out the final signal and then reset them again and repeat. So the reset circuitry, makes sure that at the beginning of every exposure for every frame, all the signals are, reset to the same baseline, and there's no effect from the previous frame to the next one. So that's the job of the reset circuitry. Now, there's different, electrical designs for to achieve, this architecture. Basically, the simplest possible APS sensor uses just 3 Mosfet transistors to build the reset and readout circuitry. And this is, as of today, this design, which is called the 3T CMOS APS. 3T for 3 transistor, and then it's a CMOS APS. It's the most most deployed architecture for these small cheap cameras that are used in cell phones and in robotics and other applications. So it's simple, but it's extremely well thought out and practical and good performing, and it's used a lot today. So it's not like we'll talk about something simple, but it's so simple that it's not useful. No, what we'll show you is actually what you open up any camera, that's actually most of them are using this architecture. Okay, so we're going to talk in detail about how each pixel works in the actual circuit. But first, let's do a quick refresher about MOSFET transistors and how they operate. So MOSFET transistor, we're gonna, at super high level, just cover the part of it that is required for understanding the CMOS APS 3T pixel. But remember that a transistor, a MOSFET transistor, it's a 3-terminal device as shown here. So it has a gate shown with G, that's one terminal, and then it has a drain shown as D, and a source shown as S. And there's lots of different things you can do with these transistors. You can operate them in different regimes. There's linear regime, there's saturation regime, there's subthreshold, and so on and so forth. And you can build lots of different circuits with different applications with this. But specifically for imaging in the 3T APS design, these transistors are mainly used as switches. Okay, so they're either on or off, basically. And the way the switch works, so as the digital switch works, is that as shown in this picture, with the 3 terminals, you can define 2 voltages. One is the voltage between the gate and the source, VGS, and the other one is the voltage between the drain and the source, VDS. And typically, there's almost no current following through the gate, so so the IG is almost zero because this is a very high impedance terminal, and that's why it's kind of shown as a capacitor here. So there's almost no current or no DC current basically going through. That's the high terminal input. And then the main current path is from drain to the source, and that's this IDS. Okay, so when we say these can be operated as switches, there's switches for that IDS. You can either have IDS go through, or you can turn off the switch and then there's no IDS, no drain source current. And the way it works, it's controlled mainly by this VGS voltage. So if this VGS is less than the threshold voltage of the device, and the threshold voltage is a voltage that is determined by, you know, the actual geometry and material construction of these transistors. It's typically sub 1 volt. It can be around mostly 0.7 volts. Some devices have lower V threshold, some have slightly higher, but that's the ballpark number. So if the gate source voltage applied is less than the threshold, there's going to be no current flowing through the device, and that's where the switch is off. And then if you have a VGS bigger than V threshold, and also the drain source voltage is bigger than VGS minus V threshold, that's where the switch is on, and then you get a current flowing through the drain source path, which is proportional to VGS minus V threshold squared. Okay, and that's where the switch is on. Okay, so that's how in the APS, in the 3T APS pixel, that's mostly how the transistors are operated. So we are going to control the VGS and then turn the switches basically on and off. And this plot here kind of shows the IDS, which is the current as a function of VDS and VGS minus V threshold. So each curve is for a different value of VGS minus V threshold. As you see, like we have 1 volt here, 2, 3, 4, and so on. And then, as we said, we're going to operate these transistors in the saturation region, excuse me. So the saturation region is the region to the right of this red curve. So that's where basically this condition is satisfied. That's for saturation. And then as you see, as we increase the VGS minus VTH for a fixed VDS, the current value is going up quadratically. If you just, you know, follow this, it goes up quadratically. This quadratic current thing doesn't really matter for the operation of the 3D APS. What matters is that we can just turn the switch on and off. You're going to just apply either VGS equals 0, which turns the switch off, or VGS, some constant value of VGS that is bigger than V threshold to turn on the switch. So we operated in like a digital mode. So that's why this expression doesn't really matter much, because it's going to be either no current going through it or some constant current basically going through it. Okay. So that's the principle of operation of the Mosfet transistor, not the full principle, but the part that is relevant to the 3T APS pixel. And now let's look at the actual pixel architecture. So this slide is really, really important. So let's make sure, you know, every detail that we talk about here is makes sense and is well understood, because this is at the core of essentially how these digital cameras work. So what we are looking at here is just one pixel, one image pixel in a CMOS APS sensor, 3T pixel. And as mentioned, so we have our PIN photodiode. So that's this guy here. And in parallel to it, in blue, we are showing the parasitic capacitance of the diode. Okay, so that's not an external capacitor component. That's why it's shown in blue. That's just the parasitic capacitance that every PIN photodiode has, right? We're showing there. And then there is 3 transistors here. One is for resetting, that's this M reset. The other one is for readout, it's called M select. And this third one, MSF, it's basically makes a buffer for readout circuitry that we'll talk more about. And then there's 2 control signals that you can apply to every pixel. There's a reset control signal, and there's what is called a row select basically a control signal. And these are digital signals, so it's either 0 or 1, right? So, and that's how we control the switches. So when the control signal is 0, that corresponding switch is off, and then you apply 1, and it turns on the switch, basically. So digital control, and let's just start with at the start of a frame. So let's say that's time 0, and here on the right we are plotting the control signals, and we are looking at the V out, which is the voltage at the output of the pixel, right? So that's V out at the output of the PIN photodiode. Okay. So at the beginning of the frame, we apply a reset signal, a short pulse. Okay, so we briefly turn on the switch, and what happens when the switch turns on? Basically, this V reset gets applied here, right? So current flows through, and we basically charge up this parasitic capacitance to the voltage that is set by this V reset voltage line, right? So you close your reset switch, and you basically set your V out to be equal to V reset, right? Then exposure starts, and by exposure we mean light is going to hit the photodiode, and it's going to generate some photocurrent, right? And if you follow the path of this current, remember now, the only way the current can flow in the circuit is by discharging this capacitor going through the diode to the ground, because this switch is closed, so there's no path here. And also, if you look at this buffer Mosfet here, as we said, the gate has a very high impedance input, so there's also no current going this way, right, into that Mosfet. So the current needs to basically discharge the capacitor, right? And so what happens if you follow V out as during the exposure, it's going to start basically discharging the capacitor until the exposure time is over, okay? And then at the end of the exposure time, we're going to apply a short pulse to the row select, okay? So what row select does is, note that it's going to the gate of our select transistor, so it's going to turn on or close this switch here, okay? And I'm going to just clean up a little bit to explain what's happening here. So this transistor, this is forming a buffer for us. And the specific configuration here is called a source follower. That's why it's called SF. And it's a voltage buffer. So what this does, if I draw it again here, the source follower, so there's VDD applied here, and then there's this V out, and here it's going to the other transistor. But the way the source follower works is that it's like an ideal buffer. So it's an amplifier with a voltage gain of 1. So the voltage at this output at the source is this Vs is almost equal to the voltage of the gate, which in our case is V out. Okay, so it basically buffers the voltage, but because this input is very high impedance, it doesn't draw current. And the reason we need this is that without this, if we directly connect our diode to some low impedance path, we are going to just very quickly drain this capacitor, and we don't want to disturb it. You know, we want the voltage of the capacitor to be only affected by the photocurrent and nothing else. And that's why we add this buffer. So the voltage here at this node is also equal to V out. That's the effect of our buffer, and that means when we apply the pulse, the control signal to the row select, and we close this select switch on this wire, basically, which we call V column, we are going to read the output voltage of our photodiode, right? So again, our V out is going to drop during the exposure time because of the photocurrent discharging the parasitic capacitor. And at the output, as soon as we apply the row select, this output voltage, which we call V column, right, it's going to get set to equal to the V out at the end of the exposure duration. So V column is V out at time t, which is the end of the exposure, which is equal to the initial value, the reset value, minus delta V. And delta V is like how much we discharged our junction capacitance within the exposure duration. After we read out, so we first apply our row select and read out the junction voltage, and then we apply another reset pulse to the reset input and set it back to reset, and then we expose again for our next frame, right? So this is like frame 1, and then this is the next frame, which is frame 2. Now, specifically what delta V is, delta V, again, is the voltage drop of the capacitor, the C, because of the photocurrent. So it's equal to 1 over C times the integral of the photocurrent IP within the exposure duration. So T going from 0 to big T. And assuming, because these exposure durations are very short, these are like milliseconds, right? IP is not going to change. It's like we can assume, you know, fixed power is hitting your photodiode, causing or generating a fixed photocurrent. So we just get IP, and the integral becomes just T. So we get IP times T over C. And remember from our discussion in LiDAR that the photocurrent is equal to the responsivity of the diode times the incident optical power. So delta V basically becomes responsivity times the optical power that's hitting that pixel times the exposure duration divided by the junction capacitance. The point is, at the end of the day, if you plug this in, the readout voltage from this column line is a linear function, is linear in the incident optical power. Right, so our image sensor, each pixel would actually measure something that is a linear function of the optical power that was incident on it, and that's a proper, you know, optical sensor, an image sensor. Every pixel measures how much light was hitting it. Okay, so here's a picture. Okay, how now you can scale this, right? So we looked at just one pixel. This is the image we looked at, and we know how that works. That's the 3T APS pixel. And now that's the magic of, you know, semiconductor manufacturing process. You can have millions of these, right? And build a big array with millions of pixels, and, you know, cover a large area, and then, you know, use that to form images. Here's a picture of an 8x8 pixel array, and the way the full, you know, image sensor works is that you see you have rows and columns of pixels, so it's going to apply a row select signal to rows one by one. So that's basically this row select signal that we had here. So when a row select is applied, basically the readout transistors or the select transistors on all the pixels in that row are gonna get turned on, and the corresponding voltages for those pixels are gonna be available on these column traces, right? And all of that go through some, you know, multiplexer or demultiplexer and get fed to the ADC. So that's how you digitize, you know, the voltages that are read from every pixel. So you do one row, and then it selects the next row, and then it selects the next row. So each row is selected, and all the columns are basically voltages are being fed to the ADC, and you basically digitize one row at a time. And there's also, of course, the reset signals that go to all pixels. So after you read all your rows and columns for one frame, you reset everything, and you do that again. So that's the basic operating principle of the CMOS APS. Now, if you look at this pixel structure here, you see there's of course the photosensitive component, which is the PIN photodiode, but you also have, you know, the 3 transistors and the wires, and these take up some of your, you know, semiconductor area. So not the entire area of your semiconductor is going to be photosensitive. And so this is, for instance, a picture showing, you know, if you look at just one pixel, you have your photodiode there. But a lot of surface area is, taken up by the transistors and the these bus traces for row select and reset and other things. So because of that, if you just, shine light on that, a lot of the light is going to hit these non-photosensitive parts of the device and basically get wasted. A way to improve that is to add micro lenses on top of all the pixels. And what the micro lens does is that it focuses rays of light, bends them and focuses them into the photosensitive area. So here's an electron microscope, cross-section image of one pixel. So you have the micro lens at the top. That's just curved structure, and you see rays of light that come through. They all get bent and they get focused into the photodiode area. Without the micro lens, these rays would have just hit, the transistors and other things, and that light would not be sensed basically. So the micro lens array, and here you see an array of them. There's like these little bubbles. They're typically, added on top of the CMOS sensor to improve the so-called fill factor, or the light collection efficiency of the sensor. Okay, so that's one. The other thing we need to talk about is that, okay, how do we actually sense color? Because basically the architecture we have so far described, every pixel would just measure the total power that's incident on it. And if the semiconductor PIN photodiode, like a silicon PIN photodiode, is sensitive to, all the visible light wavelengths, that each pixel would measure essentially an average of all colors. So we cannot form a color image out of it. We can only form a intensity image, or like a black and white type image out of it. So there's different ways that you can sense color. The most common one is by adding another layer, which goes between the semiconductor pixels and the micro lenses. So there's micro lenses on top, and then there is this color filter array that's added underneath the micro lens. So in this picture, you see you have the micro lens on top, then you have the color filter, and then you have the actual pixel at the bottom. And the color filter, it has the same pixel structure as the sensor itself, but each cell in the color array mostly just lets one color of light through, right? And so you can have like an RGB type color filter, or CFA, color filter array, and this is what happens. So you get light with full spectrum light hitting the color filter array. But if it's the red pixel, it only lets red light through, or the green only lets green through, or the blue only lets blue color through. So here is one example of the spectral response of the three different colors in the color filter array. So as you see, the blue is centered around 450 nanometers, the green is centered around 540 nanometers, and the red is centered around 650 nanometers. So each of them predominantly lets one color through, which means the pixel that is underneath each of these colors mostly senses one color, right? So then the pixels under the red CFA cells only sense red, the pixels under the green CFA cells only sense green, and the pixels under blue CFA rays only sense blue. This is one way of making your image sensor color sensitive. There's other less common technologies, just so you know, but most the cameras today use color filter. Now, there's also different designs for the color filters, like what's the pattern of this RGB cells that you want to use in the color filter array. And the most common one is called the Bayer filter. And the way the Bayer filter is designed, this is the pattern of the Bayer filter shown here. The immediate thing you would notice is that it has twice as many, like if you look at this little 2x2 square here, it has two greens and one red and one blue. So it has twice as many green cells as red and blue. And that was a design choice that was made such that this color filter array mimics the physiology of the human eye. So the human eye, as it turns out, that they're more sensitive to green color than red and blue. And then that's why this specific CFA was designed to have a response very similar to human eye, so that the pictures, the color pictures we get out of it, look natural to the human eye. So with this, what we get is that, let's say this is the original scene that you're trying to image. And then let's say it was a 120 by 80 pixel sensor. And the actual output with the Bayer filter, it looks like a mosaic. So if I zoom in here, before any processing, every pixel at the output, if you color code them, every pixel would either be just sensing red or green or blue. So it looks like, you see, again, if you zoom in even further, every pixel is just sensing the light intensity at one specific color. So it looks like this weird mosaic instead of a, you know, natural image you would expect like that. And that's something that is taken care of in DSP. So there's some interpolation that we need to do. And basically for every pixel, by looking at the neighboring ones, for every pixel, we need an R and a G and a B value, right, to get the full color of that pixel. But out of the sensor, every pixel only gives you one of the three naturally measured. So the other two colors need to be interpolated from neighboring pixels. And that's the job of the demosaicing algorithms that run in DSP. So the images that we get out of the cameras never look like this mosaic here. There's always some interpolation applied, and then we get a more naturally looking image where every pixel is interpolated to have R, G, and B instead of just one of the three. We'll talk more about demosaicing, but that's just so you know. Okay, so this kind of completes the discussion of how the digital image sensor works, or the specific one we talked about, which was the 3T CMOS APS, which is the most common type of, you know, image sensor used today. And now we are ready. So we talked about the physics and the electronics. Now we can look at the, you know, the full system architecture of a vision sensor. So this is the full architecture diagram. So as we discussed, there's always some imaging optics or lenses that we talked about, and then the image comes to focus on the image sensor plane, and we talked about how the image sensor works, and how different components that go into it. And then the readouts of all the pixels get digitized through the ADC, and then there's a number of signal processing steps that needs to happen before a final image is produced that looks natural and you know, expected. And that's the job of this image signal processor, or ISP module inside cameras. And usually, so the cameras have, you know, a hardware module, a chip that applies different, you know, signal processing steps to the digitized readouts of the sensor. And the job of that is to basically convert this RGB mosaic that you get out of the sensor to a natural looking image. Specifically, there's multiple steps that happen inside the ISP. There's, of course, the demosaicing or the color interpolation that we talked about. And there's white balancing and tone mapping. There's some denoising and image sharpening that typically happens. And also it can compress the image to, you know, require less storage. And after all of that, the final image is produced that can be stored on, you know, some storage media. Now, note that when it comes to the ISP, every camera uses different algorithms in their ISP, and most of these are proprietary to the camera manufacturer, and you don't know exactly, like, you get like what is running on your iPhone or your Android phone or your Canon or your Nikon phone or any other, you know, or your Sony phone or whatever. They are all different. Generally, they do most of these, functions that are shown here, but they can do them in different orders, and the specific algorithms they use to achieve each of these functions shown here are proprietary, and they vary a lot from different manufacturers. So we're going to high level describe, what at the functional level, what each of these blocks try to achieve. And we also talk about some very simple algorithms that can achieve those functions. But note again that we are not talking about, state-of-the-art best kind of algorithms that one could do here. We're just, barely scratching the surface. And but nevertheless, I think it's valuable to, understand what each of these terms mean, what's the goal of them, and know about at least the simplest type of algorithm that can achieve that. But if you want to work on an ISV, I do not recommend implementing the algorithms that are discussed here, because these are very simple and they typically don't work super well compared to the state of the art. You should come up with or learn much better sophisticated algorithms to achieve these. Okay, so we're going to start with color interpolation or demosaicing. Again, as we said, the natural signal that you get out of your image sensor, the ones that have these color filters, is this RGB mosaic where every pixel has just one color. And then the job of demosaicing is that interpolate the color so that we get R and G and B value for every pixel, and we get an image that looks much more natural here. This image looks pixelated. That's just because the resolution was low. It's just 120 by 80 pixels. So that it's not because of the demosaicing that it looks pixelated. It's just not that it was a low resolution image. Now, the simplest algorithm that you can do for demosaicing is just a linear interpolation. And the way it works is that for every pixel, okay, you get one of the three colors directly measured, right? Depending on what the color filter on top of it was. So you get either R or G or B already measured. So that's fine. And then for the other two colors, you just interpolate the values, linearly interpolate the values of the four or two closest neighbors to do that. So for this one highlighted here, to get the R, you average the 4 pixels at the corners of it, the R values of those. And that gives you the R for the middle pixel. The G is, again, that's directly measured for that same pixel, so no interpolation needed. And for blue, you get 2 nearest neighbor pixels, so you can average these 2 pixels, and that gives you the blue for that. And that's how you can do your linear color interpolation. Note that with this algorithm, or with any interpolation algorithm, actually, because every pixel only measures one color physically, 2/3 of the information in the final image is actually made up. And by made up, I mean it's interpolated. So it's not physically accurate. But nevertheless, because color across pixels usually doesn't change that rapidly, usually, in some cases it does, your final image can look very realistic and good. Now, with this simple, linear color interpolation, in certain cases, it can introduce artifacts in the image. Specifically, it can, if there are some structures in the image, they can cause color fringes or color moire in the final image. Notorious structures are, for instance, if you have black and white detail in your image. And here is one, if I zoom in, here's an image of like a kind of a fabric structure where it had this fine, black and white, fabric lines woven together in the image. And then the linear interpolation causes these color fringes that you can see across the image. And that's a failure of the demosaicing algorithm, basically, that has happened in this case. What can you do? Well, there's more sophisticated algorithms, of course, you can use. One way is you can fix that by applying a median filter on the colors. So after interpolation, you look at your color histograms and apply the median filter. And with that, you can remove outlier color changes. Okay, and here's one example, same picture, two different ways of doing demosaicing. The left one, I'm going to zoom in a little more on it. That's with linear interpolation. And if you look at where there's fine black and white structure, like this electrical wire line here or the branches of the tree, you would see, you know, significant color fringes. Also on the windows and other places, you would notice that. And then if you apply the median filter, so if you do the median filtered interpolation, see how much it improves. It's still not perfect, but it's significantly improved with respect to fringes and moire. Okay, so that's about demosaicing. The other thing that happens in the ISP typically is white balancing. And white balancing, basically what it tries to do, it tries to ensure that the white color is represented faithfully in the image. Okay, and why is that necessary? It's because different lighting conditions can change the appearance of colors, right? And this is something that our brains have been evolved to just take care of so well that we really don't notice it in our vision. So for instance, if you have a white piece of paper and you take it under a very warm light source like sunlight, or you take it under a very cold light source like fluorescent light, the actual color that's coming out of that paper or reflected off of that paper is going to be affected by, you know, the color of the light that was incident on it, and it's going to look very different under the two lighting conditions. But our brains just adjusts for that and balance it out such that white always looks white to us. Almost always, except if there's like some very, very weird, you know, lighting condition, like if you're in a club with, you know, very unnatural color lights, then yes, colors look different. But otherwise, in normal lighting conditions, white always looks white to us. With cameras, this needs to be handled in DSP, which means the camera needs to somehow guess or find out what part of the scene or what object in that image was white in real world. And it needs to find the RGB, the sensed RGB value for that object. And then it needs to scale all the colors, all the RGBs in the image proportionally, either up or down, such that the chosen RGB of the white object becomes 111, because RGB equals 111, that's the white color, right? So that's the job of the white balancing, is like find the white thing in the image and find the RGB value of that and scale that RGB to 111 and scale all the other pixels accordingly, so all the colors get adjusted. Here's one example. So it's a picture of a flower that was taken, and for this flower, you know, the petals were actually white, or part of them was white. And if you just this is the raw image. If you look at the raw image or pre-processed image, and you look at the actual color that the sensor sensed on the flower, the RGB value was actually 0.72, 0.8, 0.85. And this is the actual color here. It's actually gray. So white looked grayish in that image, in the raw image. And then after applying white balancing, we basically scale that to 111 and scale all the rest of the RGB values by the same scale factors. And this is the final image that you get, where the flower actually looks white as it would be in the real world, and all the colors look a little warmer as a result of the white balancing applied. Now, modern cameras try to do this automatically. So there's some automatic white balancing, or AWB, that is applied in cameras. And it's a very non-trivial task, as you can imagine, because the camera needs to somehow find or guess what that scale factor is, which means either it needs to find something that's white, and that's a very non-trivial task for in DSP, or otherwise, you know, have some heuristics. There's different algorithms. There's many of them, but here are two that are sometimes used. One is the gray world assumption, and this algorithm basically assumes that if you average the color of all the pixels in an image, it becomes gray. So that's the gray world basically approximation. So the algorithm forces the average color of the scene to become gray. So it finds the scaling factor that after that is applied, the average of all the pixels becomes gray, and that is used for white balancing. The other one algorithm looks at the brightest pixel. So it assumes that the brightest pixel you have in the image, that's the color of that is white. And then it forces that to basically become white if it's not already, and then applies the same scaling to all the pixels. But neither of these algorithms are perfect. They can fail in different scenarios. So, for instance, the gray world fails when the lighting is kind of on the extreme side of warm or cold. So, if it's very warm, like a sunset lighting, or if it's very cold, like fluorescent, gray world approximation can really fail. And then the brightest pixel approximation, it can fail when your brightest pixel is actually saturated. It was so bright that it completely saturated the sensor. So the value you're reading is clipped, basically. It's not the real value. Or if it's coming from some metallic surface that wasn't actually white, then that assumption breaks down. Here's an example where the gray world approximation failed. So this is a picture that was taken during sunset with very warm lighting, as you can see. So this is the raw image. And then with the gray world auto white balancing, after that is applied, you get this picture which with completely washed out colors. You can see this is not the right white balancing applied. So just so you know, these algorithms, they are deployed, especially the gray world still is deployed. But it's not perfect. And this is one of those cases, because the task is such a non-trivial subjective task. Actually, modern machine learning approaches can do really, really well with white balancing, way better than what these classical algorithms can do. And that's what most of modern cell phones, they have, for white balancing, they use machine learning, because you just, show them enough data with, ground truth white balance, and then just the network learns how to do it, like the human brain has learned to do it, and they can do really, really well, especially in challenging lighting conditions. Machine learning can do really well with white balancing. Okay, next thing that happens in the ISP typically is tone mapping, and tone mapping is generally speaking, it does some adjustments to colors, and that's on top of white balancing. So after white balancing is done, there could be some additional adjustment to colors, and tone mapping can be done for various purposes. Okay, sometimes it's just done for purely aesthetic purposes, just for the image to look better. And that's, for instance, if you've used Instagram, there's always, Instagram filters, and many of those filters are just different tone mapping filters that make your picture, look a little more vibrant or a little less vibrant, or black and white, and this and that. So this is not a useful, goal for autonomy, but there's other purposes for tone mapping that could be very useful for autonomy. So for instance, you can use it to improve the dynamic range of your image, or you can use it to improve the contrast of the image, and things of that nature could be very useful for sensing applications. Now, dynamic range, note that it's the ratio of the minimum to maximum intensity that the sensor can record in your image. And the image contrast is typically taken as the difference in the intensity of the pixels divided by the average intensity. Okay, so that's the technical definition of dynamic range and contrast. And when it comes to tone mapping, there's two classes or types of algorithms for tone mapping. One is called global tone mapping, and that's where basically the same function, the same correction is applied to every image pixel, right? Same function, every image, every pixel is affected the same way. Or you can have algorithms which do local tone mapping, and that's where the parameters of the tone mapping function is different for every pixel, and it uses some information from the neighboring pixels to decide, like, is this pixel, for instance, in a highlight area, in a shadow area, and things like that, to be smarter about how tone mapping should be applied. So generally speaking, local tone mapping can result in much better images, but of course it's a more sophisticated type of algorithm. And tone mapping, again, is one of those areas where many different algorithms exist, from super simple ones, one of which we'll talk about, to really advanced ones using big machine learning models and things like that. The simplest global tone mapping algorithm that actually is applied quite a lot is called gamma correction. And gamma correction, it's a very simple function. So it just basically takes the value of every pixel in the image and raises that to some power gamma, right? So you apply a value for gamma, it can be bigger than 1 or less than 1, and you apply that same function, IO equals I to the power of gamma, to every pixel, right? Now, what is the input? What is I sub I? It can be, the individual R and G and B color values of every pixel. That's one way of doing gamma correction. Or you can apply it just to the intensity value of every pixel. So there's, what actually goes into that gamma correction function. You can decide what it could be. But here's one example to show you how gamma correction can be useful. So in this case, we have an HDR, high dynamic range image, which is this input image. And this image was captured with a high dynamic range camera, but now we're displaying it on a medium like my iPad display doesn't have as much dynamic range as the image sensor. So the image looks saturated. Specifically, if you look at, the highlights of the sky, these all looks completely, saturated and white. So we need to compress the dynamic range, but the information is there, right? The actual sensor was able to capture those highlights, but I can't display it. I don't have enough dynamic range in my display to show that. So I need to compress the dynamic range of the image such that I can show all the details on my iPad, for instance, iPad display. And this is, a case where gamma correction can work, can be very effective. So when it comes to the image, as we said, you can apply gamma correction to the intensity. So this top image, you can think of it as, or another way of, instead of, just thinking about it as RGB values, you can think of it as, it has some intensity information, also called luminosity, and plus some color information, also called chrominance of the image. So you can have luminance and chrominance is another way of describing what the image is. So so we're gonna, because we want to do compression, we're going to choose a gamma value that's less than 1. So let's say here we arbitrarily chose gamma equals 0.5, and we're going to apply it 2 ways. One is we apply it to every color individually. So we raise R to the gamma, B to the gamma, and G to the gamma. And that's one way, and this is the image that we get. Note that it got the job done, right? So now we see all the details in the highlights which were missing in the original picture. But the artifact or the side effect is that it kind of looks washed out. Okay, that's the trade-off that was made. Here's another way of applying. So now we're applying the gamma correction just to the intensity. So basically we just calculate the intensity, apply gamma correction to that, and don't touch the chrominance, and then combine them again and then form the final image. Again, it gets the dynamic range compression job done, right? All those details, highlights are recovered, but the colors kind of look over exaggerated in this one. Right. Now it's kind of a matter of taste, like which one of these you kind of like better or would like to use for artistic reasons. But for sensing purposes, both of these are acceptable because the goal was to recover the dynamic range or compress the dynamic range such that on this display I can show it, and both of these gamma corrections achieve that. Okay. So last thing we want to talk about is the last step, which is typically some denoising and sharpening is applied to the images. And these are typically filtering operations, although more modern techniques, again, like machine learning, can also be used. Like you can apply neural nets to achieve denoising and sharpening, and those would do really well, especially the modern ones. But classically, these were implemented as filtering operations. And in their simplest forms, they use linear filtering. So just basically 2D convolutions with some filter kernels could be used for denoising and sharpening. Here are two examples. Here is a classical, denoising filter, which is called the Gaussian blur. So you take your noisy image. Here's like a zoomed in portion of a bigger image, and you convolve that with this filter kernel, which, as you see, I mean, it has a high value in the center, and it kind of, drops according to your Gaussian profile as you go away from the center pixel. And this is just to normalize, the sum of all the pixel values to 1, so we don't, saturate the image after filtering or dim it too much. And after applying this, it kind of, blends the value of each pixel with the neighboring ones with some Gaussian weighted sum. And this is what you get. So it gets the job done. You see, it's much less noisy in all areas. But also you lose some contrast, right? Like if you look at this portion, it's less sharp here. You get some blurriness, and that's also in the name of the filter. I mean, because we're blending the value of neighboring pixels, we get a little bit of blurriness applied to it. And here is one very simple sharpening filter. This is our filter kernel. It has a positive value in the center, and then the side pixels have negative values. So it kind of takes a difference of the center pixel with the neighbors, and it enhances edge contrast. If those pixels are at different values, it even enhances that. And that's the effect. The original picture, it was very soft, and then after applying that filter, we get much sharper features. Again, this is just to illustrate the possibility of what you can do with linear filtering when it comes to denoising and sharpening. These are by no means the best possible filters you could use, but could be useful for certain applications. Now, if you use any modern day computer vision programming library like OpenCV in Python, all of the functions we talked about, demosaicing, white balancing, tone mapping, denoising, sharpening, all of these are already, for each of them, all of these are included in these, modern libraries. And for each function, there's usually you get a variety of, algorithms that are already implemented, and you can, try them, and you can vary the parameters very easily with a few lines of code, and you kind of, see what works better for your application. So that could really be the way to go if you are not quite sure, oh, I want to do some denoising. I'm not quite sure, where to start. You can always go, OpenCV is usually my go-to package. I go and I, read the documentation about, okay, what denoising options do I get? And I try a few of them, and these are so well implemented these days that literally in 2 lines of code, you can do that. Also, well, you could use ChatGPT, of course, and it's actually pretty good when it comes to these kinds of experimentations. You can just say, hey, ChatGPT, write me an OpenCV script that imports an image in this format, and then applies Gaussian blur denoising filter with, a width of 1.5 pixels to it, and it will do it. And then you can, that can be kind of like the skeleton script that you can start. And I'm not saying you should definitely use ChatGPT, but if, you're very unfamiliar with, how these packages work, it could be a start, it could give you a place to start, and then you can experiment with different things. Okay, so this concludes the discussion about the architecture of the vision system and the ISP, or image signal processing steps, and some simple algorithms. I want to finish this chapter with just a very brief discussion about future directions in vision systems for autonomy. So I want to start with saying that vision sensors, as of today, are the most important sensors in robotics today. I mean, when it comes to sensing for robotics, vision or cameras are the king, basically. And that's for a couple of reasons. One is in terms of, the maturity of the hardware. And by maturity, I mean the cost, the size, the performance, the power, all these key metrics. Cameras today are way ahead of other sensors. They're like orders of magnitude cheaper than radars and lidars. They're much more robust. You can get much, higher quality signals and images out of them. So that's one reason, but this is not a fundamental reason, right? I mean, we know cameras because of, it started way before robotics was a thing, and there's years and years of, R&D in academia and industry behind it. So the technology is naturally more advanced. But eventually, I think other sensors are going to catch up, and yet, if not exactly at the same, point as cameras, they're going to close the gap quite a bit in terms of cost and power and performance. But also for cameras, we are benefiting from, many years of research and development and advancements in computer vision and machine learning. So most of perception pipelines today are just designed to work with images. And that really helps when it comes to autonomy, because we need to, make sense of the signals that we get out of our sensors. And already a lot of tools and algorithms exist that helps us make sense of camera images. So for instance, if you want to do classification on a sensor image, on a sensor output, for cameras, you can in 10 minutes go download YOLO V8, for instance, which is a beautiful, really high quality implementation of a classification network. And it works real time, very reliably, very good performing. But if you want to do that same task on a 3D point cloud from a LiDAR or a radar, your options are much more limited. They're not as high performance, and you need to come up maybe with your own ideas and implementations. Again, this is not a fundamental reason, right? It's just the fact that with cameras, we're benefiting from years and years of computer vision, machine vision R&D. Now, also, I want to note that we talked about RGB cameras, which is the most common type of camera, but there are also other more specialized types of imaging sensors, and some of them could be more suitable for specific tasks in autonomy. So for instance, you can get thermal cameras. They're very close to RGB cameras. They just sense at longer wave IR, which is proportional to the temperature. Of different subjects, but principle of operation is very similar. These days you can get stereo camera systems, which use basically two cameras with some distance away, which is called the baseline. And then in addition to giving the RGB image, they can also use apply some geometric methods or some machine learning methods to estimate depth in the scene. So they give you point clouds, which are RGB colored. They can be very useful, but note that typically the maximum depth that they can sense is limited, and it's a function of the baseline. So to be able to get more depth, you need to space your cameras more further apart. Also, it's a function of the resolution of the camera sensors. But stereo cameras for applications in robotics where you don't need to see that far, you only need to see like 10, 20, 30 meters, can be a very interesting option. And then you get more even more specialized types of cameras like dynamic vision sensors, where instead of just measuring, intensity, they measure time derivatives of intensity. So, and they give you these events per pixel, which could be useful for very specific tasks in computer vision and autonomy. And also, I want to note that, well, yes, camera is the most important type of sensor today, but I really believe, and in certain applications, a camera-only approach to sensing could be sufficient. But in general, that's not true. I don't believe that is true. And that's, again, because of, by now, I think at the end of the quarter, you know a lot about the physics of sensing. And with that, we know that, for instance, cameras, they'll have fundamental issues with use cases like low light, or ultra high dynamic range scenes, or low visibility scenes where there's bad weather like rain and fog and other things. And if you want a solution that can cover these use cases, or a solution that has requirements that a camera approach fundamentally cannot do. So for instance, if you need to see very long ranges, if you need to see hundreds of meters with good accuracy, even a good stereo camera system would really struggle to achieve that kind of depth mapping. And that's where you you're forced to use other sensing modalities like LiDAR, radar, sonar, and others. And also another reason to not just rely on cameras is in cases where safety is a concern, you need redundancy in your sensors such that if one modality fails, the other one can still cover you. So for that, for those reasons, I think a vision-only approach to autonomy wouldn't basically cover all use cases, but it can cover a subset of autonomy applications. And I want to close with talking about some future directions in vision sensors. So vision sensors, we have years of development for RGB cameras, and they were mostly for photography and for artistic reasons. But now that we're entering this era of robotic autonomy, there is a lot of rethinking going into what a proper camera or a vision system for autonomy could be or should be, and redesigning even the hardware to be more suitable for those types of applications. The general trend is that the future vision sensors become more intelligent, and by more intelligent I mean if you zoom into just one pixel in your vision sensor, what it does today is it basically measures light intensity at a given wavelength, basically, red, green, or blue. But now we're moving towards these more sophisticated cameras that support in-pixel signal processing. So every pixel has like a little brain of its own. Well, brain is, of course, over-exaggerating, but it has, processing capabilities of its own, and they can be individually programmed. And then by being clever about how you program these things, you can achieve like really, really sophisticated sensing tasks. So for instance, you can do very complex feature extractions right by the camera. We're not talking about ISP. Like at pixel level, these cameras can be programmed to do sophisticated things. Or for instance, if you have individual control over the exposure duration for every pixel versus the current cameras where you have just one fixed exposure duration for all pixels, you can have your cameras, do ultra high dynamic range imaging, like things like 130 dB of dynamic range have been, demonstrated, which is unheard of in classical cameras. You can do much better depth estimation, much better tracking, and other, tasks that are very relevant to autonomy. And the way this is achieved at the hardware level is, this is one very interesting way of thinking about it. So we have this axis here shown by an arrow, where as you go from left to right, your cameras, or every pixel in the camera hardware, is becoming more intelligent. And the way that is done is by having, more transistors per pixel, which means more logic or more signal processing capabilities per pixel. So at the far left, we have, our pretty unintelligent, just a 3T APS pixel and this is, the numbers are, number of transistors, order of magnitude per pixel. So this is 2 to the 1, 2 to the 2. Slightly more sophisticated than the 3T APS. We can have the log pixel, which is basically an APS with improved dynamic range, but with some trade-offs. Then you get to something like 2 to the 4, 2 to the 5 order of magnitude transistors per pixels. You can have the dynamic vision sensor pixel here, which has, you can break it down into 3 pieces. There's the photoreceptor piece, then there's this differencing circuit, which kind of takes a time derivative of intensity per pixel, and then there's some comparators. So this already can do, more sophisticated things per pixel. And then you go even further to, 2 to the 8, 2 to the 9 transistors per pixel. And then that's where you get things like SCAMP, which is a very interesting type of camera, which has almost general purpose programmable pixel. I'm not going to go into the details of it, but there's a lot that you can do with these types of sensors. Now, today, they're not widely commercially deployed, and they come with a lot of trade-offs. Main one being, as you increase the number of transistors, as you know, if you want to keep, the high resolution, that means these transistors take area, right, in the silicon wafer. So the photosensitive area becomes smaller and smaller and smaller, which means you're gonna be, your light collection efficiency is going to become lower and lower, which is a big trade-off. So because of that, I mean, these ideas, I mean, they have been deployed. They're research communities, very interesting things are being done with them. But I think there is still years away from, you know, becoming mainstream. And of course, I mean, sky's the limit. Like, I'm very curious to see, you know, as we go to even more transistors per pixel, which means we can do more sophisticated kinds of logic, where do we land? Like, could we eventually have cameras where you have, you know, a full neural net per pixel that's doing something very, very sophisticated? I don't know, maybe. Okay, so that's my take on future directions and vision sensors. And I think with this, we can conclude the chapter on cameras and vision systems and the course. I hope you found the course useful and interesting. Thank you, and have a nice summer.